So far we have been looking at various kinds of communication systems in the context of embedded platforms, but there is a point at which certain ideas of networking need to come in, and you need to be aware of certain basic concepts from networking in order to understand how communications can be scaled beyond the basic communication protocols that we have looked at so far. Now, the first question that we would ask is, why do we even need to bother, right? And the bottom line is that as you start increasing the number of devices between which you want to communicate and you want to share data between a large number of such devices, you run into problems of scaling, right? The sheer numbers start to become a problem, and the distances over which you want to communicate start to become a problem. And it turns out that the simple protocols we have, where we sort of assume the existence of wires that are directly connecting between different peripherals, the fact we assume that they are at compatible voltages, we assume that it's possible to actually share a common ground between the different devices, all of those start to break or become more problematic the larger your system becomes. And it turns out that if you cannot sort of guarantee such a thing, that you are having common ground, that you can have this kind of toggling of the voltages and so on, then you really need to rethink the entire approach by which you transfer data between devices. So a couple of definitions. The first is, what do we mean by a network in the first place? Over here we just mean a collection of interconnected devices that can communicate. So they are connected together. How are they connected? Through some physical means, and that connection is for the purpose of communication. And a protocol is a set of rules that governs the format and transmission of data between these connected devices. Okay. So with this sort of background in mind, we are going to take a little bit of a journey into some concepts of networking over here. One thing I want to emphasize, the computer networks is typically the subject of a one semester course, right? What I am trying to do over here is to sort of talk about it in 10 to 20 minutes, right, or less than that, right? So obviously I am not going to do it any kind of justice in terms of detail. What I do want to try and pick out is at least introduce some of the terminology that will allow you to understand when there is a discussion of certain kinds of networking concepts. But this is by no means a substitute for actually going deeper into the area of computer networks and trying to learn more about it. The amount of networking information that you get from this video or these lectures is not going to be enough to actually implement a computer network. At best, it will help you to understand the different components and what they are doing over there. But how they work, how they should be designed, how they should be used is well beyond the scope of what can be covered here. So with that in mind, please again understand that the terms I am bringing in over here are primarily for the purpose of a broad understanding. So some of the terms, things that you need to know, right, which are common words. There's a LAN, and a LAN stands for a local area network. It's typically a small area either inside a house or maybe inside a building, potentially inside a college campus, which is no longer really a small area, right? It could be like a few square kilometers, for example, but that's still a small enough area that you could have compatible wiring and every other thing that is there across that entire range of buildings that are there inside a campus. So we still tend to call that a LAN. A WAN, on the other hand, is a wide area network. So it's a WAN, a WAN, as opposed to a WAN, which is a vehicle and doesn't really have a place in computer networks as such. So a wide area network is at the scale of a city or a state or a country or the entire world, or possibly even including satellites and so on, right, going out of the world. But normally what we mean is typically something which is on a significantly larger scale than a LAN. So anything, the moment you hit something like a city scale, you're already calling it a WAN. In general, what we mean is it's something that is no longer guaranteed to have the same consistent style or type of devices across the entire network, and you may have to have more sophisticated inter-networking communication protocols to deal with those aspects. And then there is something called the PAN, the personal area network, which is typically of a very limited range, right, and is usually, in fact this is a relatively new terminology, but is used to indicate the set of devices that are connected involving a single person. And it turns out that in today's day and age there are quite a few, because you might, for example, have a laptop, you might have a tablet, you might have a phone, a smartwatch, there are rings that are coming in which are also connected, right. So just around the body of a single person you can end up suddenly with sufficient number of electronic items, all of which need to talk to each other, that you suddenly have a personal area network, right. Now given all of these large scale networks, there are a few things that we need to understand in terms of the topology, and the term topology of course is a mathematical term which refers to the overall connectivity of things. But over here what we are primarily interested in is the form of connectivity, or the shape of connectivity, if you want to call it that, right. So I am going to look at a couple of examples, right, and the first and foremost is actually just the general idea that if I have n different devices, right, and they all want to communicate with each other, what's the simplest way to do this? Well, possibly just create point-to-point links, right. Take wires, maybe a 2-wire connection, it could be SPI, it could be I2C, it could be UART, something of that sort, and just connect every pair of such devices, right, which means that as long as I have, let's say, 4 SPI links going out of this, or maybe 4 UART TXRX pairs going out of this one, I could actually connect to 4 different devices out here. Similarly, this one could connect to 4 different devices, right, and the bottom line is I am able to initiate a communication directly from any device to any other device over here, right. I have a dedicated link, a set of wires that can be used to communicate. Now this is a form of what's called a mesh network, right. This is not the only type of mesh network. This is a fully connected mesh network. There can be mesh networks that are not fully connected but still provide a large degree of connectivity. Now the biggest problem, which is obvious right here, is that if I have n nodes in such a system, I need on the order of n squared connections or links, right, and as you can imagine, as n increases, this scales very poorly. Up to 5 or so, you are fine, but let's say that you have gone to 10 devices, you are already talking about 100 links. If you are talking about 100 devices, it's like 10,000 links that you need to have, on the order of that, right. So it's not physically possible to actually have that many links and ensure that they are working correctly, and that they are wired properly, they all don't have any issues with signal integrity and so on, right. So meshes don't scale as well as we would like for large scale networks. Another alternative could be what's called a star network, right, where we say that the number of connections now is just proportional to the number of devices that are there on the network, but there is one magic device out here which is very heavily connected. It basically is connected to pretty much everyone else, right? And this would usually be either the central hub or a router or a switch. There are multiple names that could be given depending on how you are building it. And what happens is, if I want to communicate, let's say, between this device and this device, I can't do it directly. I have to send messages through the hub to get there, which may be acceptable. The problem, of course, is it gives you more latency. The time taken for a message to get through this intermediate hop is obviously more than if I had a direct connection between the two. On the other hand, it scales much better, right? The number of links that I have is now actually proportional to the number of devices that I have, but I do have this problem of this being a bottleneck and also being a single point of failure. If for whatever reason the central hub fails, the entire network is gone. A generalization of this idea is what's called a shared bus, right, where we have some kind of a shared medium of communication, which could be a wire, a set of wires. It could be something like what's there in I2C, right, just an SDA and SCL line with pull-up resistors and a lot of devices hanging off of that. And in fact, that is exactly what a shared bus protocol looks like, except that over here we take it to a slightly higher level of sophistication, right? We are not just looking at a pull-up resistor in order to indicate whether the bus is active or not. That doesn't scale beyond a small range as what is used in I2C, right? We are looking at things which can go to sort of hundreds of meters, if not more, and at that point each of these devices could in turn be a computer, and the kind of speeds that you are looking at could be something significantly higher. You actually want to communicate at hundreds or thousands of megabits per second, right? Now this scales the best because after all you can have stretch this out and have multiple devices connected here. You also have interesting properties such as even if this wire gets cut somewhere, the bus gets cut somewhere, there are local connections that still exist. So you are able to sort of avoid these problems of single point of failure and so on, and there are ways by which this can then be sort of stretched out and scaled in a more systematic manner. So these are some of the well-known topologies that exist for networks. There are others. What is important is that you understand what we mean when we talk about the term topology in the context of a network. Now, what are some of the concerns that come up when you are talking about the idea of large scale networks? One of the most important is what's called the scalability. How well can I increase the number, how easily can I increase the number of devices that is present on this network? And a related issue is the latency. It shouldn't be that as the number of devices increases, the time required for transferring data from one to another just sort of goes up dramatically. It should still be possible to have fairly quick communication between devices. And a couple of other things that come up are for example something called resilience, right, to something like a single component failure. As I already mentioned in the star topology, that the hub component, if it fails, the entire network fails. Or link failure, right? If there is one particular link in a star topology that fails, that's actually not too bad, because all that it means is that particular device is not able to communicate. In a mesh network, interestingly enough, even if a single link fails, I can actually still get data to that particular device because there are other ways by which I can pass the information through, right? So there are different properties of each of these topologies that give different kinds of resilience to different kinds of faults. And then you also have the notion of efficiency of the medium of use, or of usage of the medium, right? The medium is the actual underlying physical medium that is used for the transfer of data, and we would like to use it efficiently, meaning that I don't want to be wasting the resource while it is there. I want to, if it's there, if I've already put down a wire, can I sort of keep it continuously active? And if I do want to use it, is there something that's preventing me from using it all the time? So such concerns are also part of the process of designing a network protocol. Now there are a few things that come up in the context of how we actually transmit data. One is the medium itself, and at a very high level you can classify this into two types: wired medium and wireless medium. So far everything we have looked at is a wired medium, right? So the UART, SPI, I2C, one wire, all of those are wired media. But there are wireless media that you are no doubt familiar with. At the very least you would have heard the terms Wi-Fi and Bluetooth, right? And of course 4G or 5G or whichever is the communication that is there on your phone. Now wireless we will get to later, but clearly there is a very significant difference in qualitatively between these two. Now there are modes of transmission which we have already discussed at one point. The simplex transmission basically means it's only in one direction. There's a master, there's a slave. The master can talk to the slave and that's it. There's no return data coming back. Now that's very rare. That's only when you just want to send commands and so on. You could also have half duplex, for example like in I2C, where at any given point in time only one of the devices is capable of pulling that SDA line, which means that it can only go either the data is going from master to slave or from slave back to master, and not both at the same time. Or you could have full duplex, which can potentially transfer data in both directions at the same time, right? And that's obviously the best use, but typically requires extra overhead. So even in something like a UART, you need separate TX-RX pairs for having data going in both directions at the same time. Now one other aspect which sort of is a key concept in the area of networks is the idea of what kind of connection is being made, right? And there are basically two types over here. There's something called the circuit switched connection, which if you think about it, it's like when you make a telephone call to somebody, strictly speaking, your underlying model of the system is that you have a dedicated connection to that person, right? There is a circuit switched which directly says that anytime I speak, my voice is going directly to that person, but that's actually only an illusion. It's not that every bit that you create over here is directly going through to them. But on the other hand, with something like a UART, where there is a physical wire between 2 points, you actually have a circuit switched connection, right? Or rather, it's not even a switched connection, it is a established or dedicated circuit. The switched connection comes from the fact that it may be possible to take a certain set of wires and change them, maybe connected from one device to another. But as long as I have a permanent way by which the set of wires is physically sort of switched between two different points, I can call it a circuit switched connection. It's basically a dedicated link. The alternative is what we call a packet switched connection, and the idea behind packet switching is one of the core concepts that allowed networks to develop the way they have up to today, right? Which is that you break the data that you want, rather than trying to send it all across a dedicated link, you somehow break it up into small packets and then send them out, and hopefully they are received and can be reconstructed at the other end, right? There are a few different terms that again come in over here that you may encounter. You don't need to know each and every one of these things. You have many different types of devices that are part of a network. There are things called terminal equipment, which is typically end users. It could be your computer, it could be your phone, it could be a watch, right? There are access points, which would typically be a Wi-Fi router or something else that allows you to connect to the network, right? And which in turn is also connected onto the network. There are switches that in a lot of cases you may not even get to see, unlike a Wi-Fi router, which is a form of switch, right? There are other network level switches that you probably don't even get to see on a regular basis, that actually take care of collecting data from multiple sources and then forwarding them to an upstream that actually handles switching them in the correct way. And then there are routers. A Wi-Fi router is a very sort of simple example of a router. These provide advanced connectivity and allow you to sort of link large different networks together. So all of this is sort of just in terms of terminology. There are other things that you will probably come across when you read about networks. In particular, there is something called the OSI, the Open Systems Interconnect, which has defined what's called the OSI 7-layer model of networking. Now, in a lot of cases, yes, there is a place where the OSI 7-layer model has some utility in terms of understanding how a network works, but for a lot of practical scenarios you can get by without needing to go into the 7-layer model at all, right? Some of the terms that you will encounter and that you may sort of need to have at least a high level understanding of is, what does it mean by physical layer, what is this thing called the MAC layer, and what is the network layer. But beyond that, you really don't need to worry too much about the different layers of the protocol. Okay. So as I said, packet switching is one of the core ideas that made networking feasible and useful, right? And the idea behind packet switching is just this. Let's say that I have to transfer some amount of data between two devices A and B, right? One possibility is that I have a dedicated connection between them, and that connection has to handle all the data that is being transferred, right? If I have a physical link, that is, if I have a pair of wires, let's say, that connects between these two, that physical link is occupied for the entire duration of the transmission. It has to be available. If something goes wrong and the link breaks, that's it, I have lost the connection between these two, right? Now, another way of doing this is to take the same amount of data and to say I'm going to break it up into a number of different packets. I'll call them P1, P2, P3, P4, and maybe I don't even have a direct physical wire between A and B, but A knows how to talk to C and A knows how to talk to D, and what it does is it just takes these packets and sends some of them to C, some of them to D, but with the information in each packet saying my final destination is B. So by doing this, what ends up happening is C gets this packet P1, it sees that the final destination is B, it knows how to talk to B, it sends it across. It gets P3, it also sends P3 across. P2 goes to D, which again forwards it to B, P4 goes to D and again that also forwards it to B. Now B could get these packets pretty much in any order, right? It might get first P1, then P2, then P3, then P4, in which case great, you got it in exactly the order that you wanted. Or it might be that these links were very fast and it got P1 and P3 first, and after some time it got P2 and P4. But as long as I have some information about what is the order in which to reconstruct them, I can put it back into the correct order. Worst case scenario, I might even find that while sending P1, P3, maybe P1 got corrupted, some bit went wrong. So I had to resend P1 again after that, which means that finally at B I ended up getting in the order P3 and then P1. But even that doesn't matter because I know how to reconstruct it, right? So this reassembly of packets at the destination means that I have now suddenly taken this large amount of data, broken it up into small manageable chunks, and I have got a tremendous amount of resilience in my system because I can basically send it across multiple different links. Even if one of them fails, it doesn't matter, my packets will still find their way through to the final destination. I can use multiple paths, I am resilient to link failures. The important thing is I need some kind of an addressing mechanism, right? Unlike in a UART where I know that when I toggle the TX pin, it's going to this particular target. Now each packet P1, P3, P2, P4 needs to carry along with it the information that it is meant to go to B. So B needs some kind of an address or a name or some way of identifying it, which allows the overall network, things like C and D and so on, to say, okay, a packet has come to me, but it's not meant for me, the destination is somewhere else, but I know how to send it in that direction, let me forward it there. That is the process of routing, right, which basically says that each of these intermediate steps, C and D and so on, can look at the address and say, okay, I received this packet, but it wasn't meant for me, but I know how to send it on its way. Let me send it forward to the next path. Even if I don't know how to make it reach B directly, I know how to send it to someone else who can eventually get it to B, right? And that is a tremendously interesting concept which allows very large and very reliable and resilient networks to be built. Okay. Now a very basic example of this is something called Ethernet, which is actually almost at the physical layer, right? It provides some kind of physical layer description in terms of how the connectivity is to be handled, but Ethernet actually sort of plays its main part in something called the MAC layer, the medium access control, right? The primary sort of role that it plays is in terms of how are these different devices supposed to access this shared medium, right? Now what happens in the case of Ethernet is that each and every device that you have over here is given an address which is a 48-bit value, okay, and in principle at least this Ethernet address is supposed to be globally unique, meaning that there are no two devices in the world that have the same Ethernet address. Now that's in principle, and the reason I say that is because although the original idea behind Ethernet was that literally at the time of manufacture, the manufacturer would put in an Ethernet ID and nobody would ever be able to change that. In practice nowadays it's actually possible to change the Ethernet ID because it's usually stored in some kind of flash memory that can be updated if necessary, right? Now how does Ethernet work? There are 48 bits which roughly translates into around 10 to the power of 14 addresses or so, which is quite a lot, but at the same time given the rate at which devices are being added on to the Internet of Things, it still means that you might run out of addresses at some point, right? Unlikely. So at least at this point in time we are still fairly safe. It is possible, at least theoretically, to assign a different Ethernet address to every single device that has been created, right? Now what that means is when I create such a network like this and I create all of these devices that are connecting to that network, I need to have some way by which I can find the address of my destination. I can't sort of store the address of every possible destination, there are too many of them. Let's say that I am in a building and I know that there are 100 other computers in the building. It may be possible to actually store the Ethernet address of every one of those, and that's pretty much how the original Ethernets worked, right? But there are alternatives, which is that if D1 doesn't know exactly the address of D2, it only knows some other way by which, to get to it, it has a name or something associated with it, it can broadcast a message onto the bus, which everyone else, D2, D3 and others will read, but only D2 is going to respond to it by saying, hey, I think that's meant for me because you seem to have my name somewhere over there, right? Now, the process by which this happens, that D1 finds out D2's address and so on, is slightly more complicated. There are things called the address resolution protocol and so on which handle that. Again, we will not get into those details. You don't need to know how that works. What is important is at this point to understand that the Ethernet MAC address is supposed to be a globally unique identifier, and at least in principle you can use that directly to send something from one place to another, right? So Ethernet by its very nature is well suited for LAN size communication networks, meaning that within a building, perfect, even on campus, because it can go up to hundreds of around 100 meters or so in length. It's designed for that kind of distance from an electrical point of view. What I mean is the voltages and the type of wiring are designed such that they will actually go reliably over those distances, and you can actually hit tremendously high speeds. Now Ethernet is defined up even more than 100 gigabits per second. Ethernet exists. Now in practice you probably have 1 gigabit per second, and this is common, right? 1 gigabit per second Ethernet inside a building is fairly common at this point in time, and at those speeds you can probably go to several tens of meters at least. So definitely connect between rooms in a building at those speeds. Okay. Now Ethernet is fine as long as you are inside a building, or maybe even inside one campus, maybe a college campus or a community with many houses in it and so on, right? But there could be other kinds of networks. Maybe there is yet another campus where the connections between these are not through Ethernet. Maybe for all you know, this is a full mesh network consisting of SPI communication protocols, right? We don't know, we don't care. The point is, I would like to have some way by which I can communicate between all such different blocks. And that's where the concept of internetworking comes into play. What internetworking says is, I need some way by which an Ethernet over here and an Ethernet over here and some other network over here can all communicate with each other. It is literally, it may need to sort of communicate between Ethernet and non-Ethernet protocols, because Ethernet is just one of the mechanisms I can use in order to communicate between devices, right? But what I am saying is, I would like to be able to communicate across such networks, right? And I would also like to go to longer distances. It is literally something called an inter-network communication protocol, which we know as the internet, right? So what we usually call the internet actually refers to this inter-networking protocol, which allows us to communicate between different kinds of networks, right? It uses an addressing mechanism very superficially similar to what Ethernet uses, but similar kind of concepts. You still have the idea of an address. You need to identify the address, and based on the address the routing or forwarding will be done, but the actual underlying mechanisms are different. And the best part about it is that from the beginning it was designed to adapt to different kinds of end networks. So it really doesn't care what kind of networking you use between the different devices over here, as long as finally either they or at least one of them, right, which basically acts as your end router, is capable of talking the internet protocol, right, and translating between the data that comes in here and what is happening here, and the data from here and what needs to go out over here. Okay. So the term IP is something that again you will commonly come across. It stands for the internet protocol and is used in order to connect different networks together. And IP address basically refers to that number or some set of bits that is used in order to identify end devices, right? The most common version of it that we use even today is what is called IPv4, the fourth version of the IP protocol, the internet protocol. IPv6 is very common again these days, especially some of the mobile communication platforms have played a very important role in popularizing them. At end campus networks and on the home Wi-Fi routers, we still tend to talk about the IPv4 addresses, but for the most part IPv6 has a number of superior characteristics. It's a bit harder to sort of understand and implement, which is why it has not sort of become mainstream completely, although just the fact that it is deployed on such a large scale means that it is by no means a sort of niche application. Like I said, I'm not getting into the details of how either IPv4 or IPv6 work. The only point that I want to make over here is, especially when you use something like a Wi-Fi router, you would have come across addresses that look like this, right, 192.168 and so on. And the reason why these exist is that the IPv4 addresses are only 32 bits. They are not 48 bits like Ethernet, they are only 32 bits, which translates into around 10 to the power of 9 addresses. Now, there are already more than 10 to the power of 9 human beings in the world, right? And there are almost certainly more than 10 to the power of 9 electronic devices that need to communicate, right? What that means is the idea that I can now assign a unique address to each device is no longer possible with IPv4, and therefore what ends up happening is that pretty much every home Wi-Fi router, what it does is it hides the devices behind it, and it has just one address that is visible to the outside world, right? And it translates the addresses of all the others in such a way that the outside world doesn't really know that it's talking to 5 different devices inside. It just thinks there is one router out here. Now this NAT or network address translation happens at multiple levels. It is not the most scalable or friendly way of creating a network, but it works, and therefore it's still very popular, right? Now all that is more from the point of view that these are just something that you might come across when actually dealing with numbers. The important point is, when you see an IP address like this is what is called the dotted quad notation. It's basically 4 8-bit numbers that are being specified out here, right? So the important thing you need to understand is each of these numbers is a number between 0 to 255. You cannot have a number over here which is more than 255, that's meaningless. It's supposed to be an 8-bit number. It's also just an unsigned 8-bit number, so it's a number between 0 to 255. And there are 4 such numbers which basically adds up to a total of 32 bits. That is just a notation that makes it easy for human beings to understand a 32-bit number. That's the important point to keep in mind over here. Now, IP by itself, like I said, it already has a notion of addressing. How it works is that there are a whole lot of complex routing protocols that are able to pick up those addresses and translate them into information that is used in order to actually route packets. Again, well out of the scope of what we can cover in this course. A few more bits of terminology, right? A large part of this entire section is just boiling down to a bunch of terms that you need to at least be aware of. You need not sort of learn them by heart, but knowing what they refer to will help you to understand many other things in context. DHCP stands for something called a dynamic host configuration protocol. Where this comes into play is, let's say you have a new device that is connecting to a network. There is some system or mechanism over there that allows a server somewhere on that network to automatically configure this new device with an address and tell it something about what the network looks like, right? IP is the term used for the internet protocol, and this is basically going to describe the underlying structure of the packets and the addressing that is used for your communication. TCP stands for something called transmission control protocol. It's a reliable end-to-end mode of transmission, possibly with high latency, right? And UDP stands for the user datagram protocol, right, which is lightweight, meaning that you just transfer data without any guarantees of actually getting through to the other end. Now, why do you need to know these two terms? Because in the context of IoT or Internet of Things applications, you will find that people talk about UDP being better than TCP simply because of the fact that it has less overhead, but TCP being more reliable than UDP because it guarantees the delivery of packets at the other end. Beyond that, how do they actually work? At this point we are not going to get into it. We are just, the sort of high level takeaway is the fact that this is reliable transmission, this is lightweight and probably faster. Okay. So to summarize, networks are basically by themselves a very vast area of applied research. There are a few concepts that an embedded designer should be aware of. The most important being the fact that there is a notion of packet switching, right, and that uses the concept of addressing in order to actually communicate packets. There is a physical layer which is the actual underlying electrical circuitry which transfers data, versus the network layer which handles things like the abstractions, the addresses, the switching, the routing and various other things that actually get packets from one place to another. There are a bunch of different physical layer or medium access layer protocols such as Ethernet, Wi-Fi, Bluetooth, again terms that you would have heard of, versus IP, which is used for the internetworking, that is connecting different protocols together, right. And finally, there is also the TCP and UDP are terms that as an embedded designer you may come across. The main takeaway is that these are the lowest level internet protocols, on top of which many higher level protocols including HTTP, FTP and so on are built, which allow you to actually transfer data in a systematic manner.